So, Lecture 3.1, Transient Response Characteristics. So, we define 4 transient response characteristics, all defined in terms of the system's step input response. Okay? So I told you way back when we introduced the 3 so-called singularity functions that they were also called characteristic inputs, right? Back in the system dynamics portion of the course. And they were the Dirac delta function or impulse function, the step function, and the ramp function, right? And those are used extensively for characterizing a system's response. Now, the gold standard for transient response characteristic evaluation is the step input. So what we think of is the input 0, and then when the time is, it goes from negative time to 0, we step up to a single, 1 unit of whatever input we've got. And so that's the unit step function. So that response, which we can see an example of, an illustration of for some system, given here, is it's going to go from often 0 to the final value in time, and we want to characterize how it does that. And that's what this transient response characteristics chapter is all about. How do we characterize this transient response? How do we come up with some parameters that describe it well for us, and that we can use to sort of numerically evaluate one controller's performance versus another controller's performance? So we're going to we're going to define 4 characteristics, and the first one's called the rise time, which is the duration from the time the response reaches 10% to the time it reaches 90% of its final value. So from 10% to 90% is this time interval, TR, and that is characterizing how long it takes for the system to respond to this input, right? So it's a pretty good measure of how quick the control system responds. So you might have criteria like you have to have a rise. Well, you might have. So you remember the design process comes from maybe like features that you want to see or customer. I guess like desired features, and you take that down to what are the engineering requirements, which are hopefully measurable things you can judge your design on. And if you meet all the requirements, your design should meet the customer's needs, is the idea, or your technology goal. It should meet your technology goal. So this this rise time would be an example of a requirement. Might be that your rise time be, say, less than 500 milliseconds for some maybe I don't know, measurement control system or something like that, so that you can have maybe a very quick response to some change. That would be an example of an engineering requirement that would say, oh, okay, you have to have a rise time of less than this. So that would be your goal for your control system. Okay, so then the next one is the peak time, which is the time interval from 0 to the time when you either come to your first peak, or sometimes it's defined relative to the tallest peak, which usually they're the same. So it would be unusual if it wasn't the case. So it's equivalent. So the peak time is kind of a similar metric. The rise time and the peak time are related, right? There's no peak time defined, though, if there aren't any oscillations. The peak time is infinity, I guess you could say. Like, it takes an infinite amount of time for it to approach its steady state value. So the steady state value would be the max if there's no oscillation, and so that would happen at infinity. So it's not really useful unless there's some oscillation. So unless you have a system that's underdamped, where you have oscillation. But the rise time would still be defined. So that's one case in which the rise time is better than the peak time, but usually the peak time and the rise time are used kind of interchangeably for metric. There are some instances where peak time is interesting in and of itself, as opposed to the rise time, but it's very rare. So we've got those two, and then the last two are actually the ones that are used the most. So the percent overshoot is the next one. It expresses the amount the response overshoots its steady state value, expressed as a percentage of the steady state value. So this is the formula. We take the YP, which is going to be the peak here. So YP is the Y peak. And we subtract the steady state value, okay, which is the value that the envelope is approaching as time goes to infinity. And we subtract that off, and then we divide by the steady state. So it's a percent difference, multiplied by 100 to get the percentage. And that's the percent overshoot. So this one, I would say this graph, I don't remember what it was that I plotted, but I think it's like a second order system with maybe 30% overshoot or something like that. It looks like about 30%, just this distance divided by this distance. So something like 30%, 25 maybe. And that one's really useful for a lot of designs. We care about how much it overshoots, right? I mean, the one that we've talked about before is like the elevator. Having any overshoot in your elevator when it gets to a new floor is uncomfortable, right? You guys have all been in that elevator, that old elevator where it does this when you get to the floor, and you don't like it. I'm just telling you what you like and don't like. I don't like it. I don't like it. Probably you don't like it either, but so overshoot. So that really matters in certain designs. Sometimes it doesn't matter as much, but we will use that as one of the criteria. And then the final one is maybe the most common one that's used, and that's the settling time. So settling time and percent overshoot are used a lot. So the settling time is the time at which the response reaches and thereafter remains within plus or minus 2% of its steady state value. So that's this gray band, and I don't know if you can see that very well on the screens, but what I've plotted here is the steady state value, and then this gray band is plus or minus 2% of that. So the gray band is telling you if you're within this after a certain point, you've pretty much settled down into your steady state, but it's never going to stay at steady state until time goes to infinity, right? Never going to quite stay there. So you define a bound, and it's an arbitrary choice, the 2%, but it is a standard that's used throughout the literature that I've ever seen on what the settling time means. So what you look for is, okay, it goes into this band right away, actually, but then it leaves again, so that's not it. So it leaves again, but this time it comes in, but it doesn't quite leave the bounds this last time. It stays within. So we use that as the settling time. Whatever time that occurs is the settling time, the amount of time from 0 to that time. So the settling time tells us how long it takes for it to really get close to that final value, that steady state value. So those are the three, and those are the three that the four. Those are the four that we're going to consider for transient response performance. Notice a couple of things. 3 of them are time, and one of them is percent overshoot. Now, we have a linear system, so let's reason through. So this is for typically a unit step. This is what I plotted this for, as a unit step. But actually, let's reason through if it matters if the unit step is scaled by any number. So like 5, let's say. So you do 5 times a unit step. If you scale that step input, are any of these going to change? Any of these performance characteristic is going to change. So the time domain ones aren't going to be affected, and I'm going to argue that because we have the principle of superposition, right? The principle of superposition says that for a linear system, if you scale the input, which was a unit step function, by a factor, let's say 5, then that's equivalent to scaling the output by that same factor. So we would scale this graph vertically. If you multiply something, some function by a number, you just stretch it vertically, right? So that wouldn't affect any of the time intervals. So that's the horizontal axis. So you're not gonna change that at all. So the time, the settling time, the rise time, and the peak time all stay the same if you scale that step input. And the same is actually true for the percent overshoot because it's expressed as a percentage of the steady state value. So the steady state value would also be scaled by 5, but so would the peak, and so would the other factor up here, the other y steady state. So that cancels. So these are all parameters that are valid for any step input. And so they characterize the system not just for a unit step, which is pretty important. Now, if you have a nonlinear system, which we're not considering very extensively in this class, if you have a nonlinear system, that is not necessarily the case. Okay, so nonlinear systems are hard to think about actually, because we think everything's linear. That's actually one of the reasons why it's so hard to talk about climate change, because climate change is a system that's a complex system that has nonlinearities in it. So you guys have probably heard of like this tipping point concept. It's just, you hear it in the news sometimes. But we don't know, but we suspect that there's a tipping point where if you go too warm, you don't go back. So that's the thing that nonlinear systems are like. We're so used to linear systems where we put in x and we get out y, and then we put in 2x and we get out 2y. But there's a thing with nonlinear systems where if you go over a threshold, suddenly everything changes. And that's it's so hard to think like that. So it's important not to convince ourselves that everything's linear. And we do that in this class. We do it in a lot of classes where everything's linear, right? It's important to remember that a lot of systems aren't linear, and as long as you treat them, if you treat them within a certain domain, you can treat them as linear. But if you go outside that domain, sometimes all bets are off. So you got to be a little bit careful with this linear thinking. So linear thinking in this, we can characterize all of our linear systems using this unit step or 5 times unit step, no problem. Either way is fine. But that won't be true in a nonlinear system. So don't find a nonlinear system, put in a unit step input, and think that every step will look like that, because it won't necessarily. So that's it's just a caution on our assumption that we're always making in this class. Well, we're not always making. We've talked about some nonlinear systems, but we frequently make this assumption of a linear system. Just be cautious with that assumption. Make sure it's actually valid. I mean, it's not a bad assumption in a lot of cases, but there are certainly cases where we run into things that are not linear. And if you use linear thinking with it, it's going to lead you down the wrong road. So unintuitive things are difficult, and nonlinear things are not intuitive to us typically. Nonlinear things freak us out. So, all right. So there's my little nonlinearity spiel. Didn't know where that came from. No, it was relevant. It was relevant. All right. Any questions on these criteria? They're pretty simple definitions, right? For any given system, it might be hard to find analytically what this is, but if you have a system's response, I mean, you could just dice it up and see where it crosses this threshold, that threshold, and you can find the values.